following is an energy diagram for electronic transitions in the Bohr hydrogen atom. That's what it looks like. Part A, explain why the energy levels get closer together as they increase. Provide mathematical support. So we learn already as you go farther away from the nucleus, the radius, okay, of the atom, there's less and less of a difference. And so you see that here. Right? There's a big gap between energy levels 1 and 2, and then the gap gets smaller, and then even smaller, and then even smaller, and then at some point it's just very, very similar to each other, which is why the filling, part of the reason why the filling, the alpha filling rule gets really fuzzy as you get farther out. There's all kinds of rules are broken out there. All right, that's another topic. So Bohr related, or you can calculate the energy of an electron at any one of these quantum levels, right? You quantize these energy levels, right, by negative 2.178 times 10 to the negative 18 joules, 1 over n squared, where n squared is the one of these energy levels. Right, so if you notice in this equation, this here doesn't change. That's a constant. The only variable is there, and that's at the denominator of this multiplier. Right, so that's all we need to focus on. So let me get rid of this. We don't need that. We're just going to compare the 1 over n squared part. Okay, so if we go from like n equals 1, all right, n equals 1 to n equals 2, all right, let's see what that difference. Oops. All right, n equals 1. Let me do this today. There we go. N equals 1 to n equals 2. Okay, so 1 over, I'm just going to go lower to higher energy level. You can do this, you can do it the other way if you wanted to. All right, 1 over 1 squared is 1, minus 1 over 2 squared is 4, right? I'm just going, because that's the part that changes, right? That's what we just said. All right, so I'm subtracting because I want to know the difference. And we're going to compare those differences. That's what the question is asking us to do. All right, so that's going to be 0.75 in whatever arbitrary units if you want to. We're just comparing, so it doesn't matter. All right, so that distance, let's say, is 0.75. Okay, so since they're using red here, I'm just going to use a red color here. So from n equals 2 to n equals 3, let's see what that difference is. Right, so 1 over n equals 2 is 4, right? Because n squared is 2 squared is 4, minus 1 over 3 squared is 1 over 9. All right, I'm going to need a calculator. I'll be right back. All right, here we go. 1 over 4 minus 1 over 9. All right, so you're going to get something much, much smaller. So 0.14, let's say. All right, 0.14, and so that is like that distance. Right, and that is that distance. So I don't know how many times is 0.14 going to 0.75, right? So 30, about 5 times, a little more. So that's about right. This whole area is about 5 times larger-ish than that. If the diagram is drawn to scale, let's do one more. Right, so from n equals 3, which now we're going to fit this in. Oh, here we go. Oh, and I'm using green. All right, 3 to 4. All right, that gap is so tiny I can't even fit. So here we go. n equals 3 is 1 over n squared, right? 3 squared is 9. Sorry, Lincoln about to get towed. Okay, minus 1 over 4 squared is 1 over 16. Calculator, go back to that. 1 over 9. You need to move your Lincoln. Playoffs. We need all the spots. 1 over 16. Is that good? Yeah. Right. Again, much smaller. So that's 0.05-ish. Okay. So that's this distance here from 3 to 4. Right. That's a fraction of that, which is a fraction of that. Yeah, they're getting much smaller. And so you can say that in words, right? Because the denominator is getting bigger, or for every time 1/n gets bigger, it's that whole term is going to get smaller by 1 over however much it's getting bigger squared. All right, part B, verify the colors given in the diagram are correct. Provide mathematics. No, that's a lot of work. Verify red, green, and blue are correct mathematically. All right, I'll be back. Definitely going to speed this up. All right, so this is copied and pasted from your reference sheet. This is what you would use from to calculate the transition energy of electronic transitions in a Bohr model, which is an atom with 1 electron, right? From n equals final to initial, final minus initial. All right, we're going to have to do this, and we already know what wavelengths to expect because this is the model example we used to introduce this chapter. So let me actually get that, and I'll be back too. All right, I'm sorry, I couldn't find those notes. So if you recall, when we first learned about the problems that Rutherford's model had, and all of physics at the time couldn't explain why when you passed, so here's a lamp. Let's say, well, this one's going to have hydrogen because that's what this example is about, right? You pass that. Let me do it the way I did it in class. All right, so here's a hydrogen lamp, okay, and you put high voltage through it. It's going to light up, and you take that light and you pass it through a slit, like maybe from a cardboard box that we made, and you pass that light, which comes through that slit, that slice of light, and you pass that through a prism, right? Then you're going to get a wave. Well, you are going to get waves. You're going to get a line there. That's going to be 656 nanometers, right? And then you're going to get this green, somewhat a little more distance away, and that's going to be 486 nanometers, right? Then you're going to get this blue a little bit closer, and you're going to get 434 nanometers, and then the purple is going to be 410. Hold on. So this is unique to hydrogen. All right, so this question is asking, right, why, show us mathematically how you get these numbers. So we're going to speed this up. So you're just going to use that equation. And so let's show mathematically how we get 656. I'll do this in red. Right, so the change in energy, man, this is gonna be your bonus question on your test, is use this equation to solve energy in one of the transitions. So here we go. All right, Z is gonna be 1 because hydrogen only has a 1 proton. But this would work if it was an ion of some higher. All right, let's go 1 over n over 2 final. Okay, so it's going to end up, all right, this is going to be from n equals 3 to n equals 2. All right, here, I'll show you. All right, 3 to 2. All right, it's Balmer series, all of these. All right, 3 to 2. So final is where it ends up in. So that's going to be 1 over 2 squared. Man, it's busy night. Okay, so where did it start? N equals 3. 3 squared is 9. All right, we're just going to punch those numbers in a calculator. We'll get that, that change in energy for that transition. It's going to be a long video. Okay, let me do that in parentheses first. So 1 over 4 minus 1 over 9, because 3 squared is 9. Let's get that. We're going to multiply that by negative 2.178. All right, so that's the whole. Let me do that again. I forgot something very important. All right, that number times negative 2.178 times 10 to the negative 18. Yeah, that might make a difference. All right, so there's the energy transition. Energy involved in that transition. I just lost it. 3.025. Negative 19 joules. All right, now it doesn't matter that it's negative or positive, because when we're looking for a wavelength, it can't be negative. It can't have a negative wavelength. All right, so this is your change in energy. Forgot to put that there. All right, so now we know that energy is also related to Planck's constant times the speed of light over wavelength. Now we can rearrange that. All right, to get wavelength is equal to Planck's constant times the speed of light over energy. And we know all of this now. Just time to plug and play. I'm going to do all this in a calculator. Planck's constant is, by the way, 6.626 times 10 to the negative 34 joules times seconds. Speed of light is, let me make some more space. Speed of light is 2.998 times 10 to the 8 meters per second. Seconds are going to cancel out. Well, let's do the energy term too. Do them all at the same time. All right, all over energy, that's what we saw for earlier. That goes down there. 3.025 times. This is not rounded, so we're good. Don't round until the end. Joules cancels out, seconds cancels out. We are left with meters. That's good, because that's what you can use to measure wavelength. Now let's go back to our calculator and punch these numbers in. 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8 divided by 3.025 times 10 to the negative 19. There's our wavelength. Perfect. Put that in nanometers, right? You know how to do that? There it is. We just confirmed it. All right, so 656 nanometers. 606.6. Close enough. 656 nanometers, and that's what we said. All right, so we just confirmed that. Now I just got to do this. Right? Just confirmed. Now we got to do this for the green. Oh. And the blue. Okay. Let's do green. Change in energy. Negative 2.178 times 10 to the negative 18 joules times Z squared. 1 over n final squared minus 1 over n initial squared. All that stuff is on your formula sheet. This is going to be 1. We can ignore that because hydrogen only has 1 proton. All right. So I'm just not gonna rewrite all that. So we're going from color. Going to 4 to 2 now, right? We just went from 3 to 2, that's going to produce red. 4 to 2 is going to be slightly more energy. This is going to be the green light, right? So 1 over final is going to be, they're all going to end up at 2, right? These are your Balmer series to produce the visual light that we can see, such as green, red, and blue. So that's going to be 2 squared. And it's going, this time is going to start at 4 squared, and so that's going to be 16. That's the only thing that changes. I should have saved it in my calculator. All right. All right, again, I'm going to do the stuff in parentheses first. So 1 over 4 minus 1 over 16. All right, there's that term in parentheses. I'm going to multiply that by 2.178 times 10 to the negative 18. And I missed the negative sign at the beginning. But again, it's not going to matter because wavelength has to be positive. All right, so there's my energy. I'm not gonna write all those digits because it's saved in my calculator. So 4.08. Right, so 4.08 times 10 to the negative 19 joules is the energy associated with that transition right there. Not that. N equals 4 to N equals 2, which is the one that produces the green light, which is why I'm using the green marker. Right, now we can use a little more space. Okay. Right, so go this way. E is equal to Planck's constant times C over wavelength. Rearrange that. Yeah, wavelength is equal to Planck's constant times C over energy. And now we can just plug in all these numbers in our calculator. All right, Planck's constant is negative 6.626 times 10 to the, wait, that's not true. All right, 6.626 times 10 to the negative 34. Don't make a mistake here. Pressure's on. Times 2.998 times 10 to the 8 meters per second divided by energy we just saw for that. That's up here somewhere. Right there. Beautiful. Let's make sure this looks good. Looks good. Well, no, it's good because it should come out to 486 nanometers, and it does. All right, so we just confirmed that. 486 nanometers, right? Because 1 nanometer is 10 to the negative 9 meters, right? So that's what you're doing with that number in the calculator. Finally, it's not too bad. All right, let's do this for the blue. So we got a negative 2.178 times 10 to the negative 18 joules times Z. That's going to be 1. 1 over. It's going to end up at 2 squared, right? So they all do. Balmer series. Minus this time is going to go from 5. N equals 5 squared, which is 25. All right. So the energy, this is all related to the change in that energy change in that electronic transition from energy level 5, this is N equals 5, to N equals 2, which produces that blue line, which has a wavelength of 434. Let's see that 434 come out of our calculator. What am I doing here? Got distracted. I'm getting lonely. I want to go home. What am I doing here? Energy? Okay, let's punch these numbers in our calculator. Here it is. Negative 2.178 times. Now, I'm not doing the parentheses first. I just realized. It's good to mix it up. Times 10 to the negative 18. Okay, now we'll multiply that. Now we're going to need some parentheses. 2 of them. 1 divided by 2 squared is 4. minus 1 divided by 5 squared is 25. Double parentheses. Looks good. All right, so there is our change in energy, 4.57 times 10 to the negative 19 joules. Now, let's plug that in. All right, so I don't have to derive this again for you. You remember, right? It's Planck's constant times C over energy. We just did this twice. All right, let's plug these numbers in. Planck's constant is 6.626 times 10 to the negative 34 times speed of light is 2.998 times 10 to the 8 divided by that number. We just got energy right there. Boom. Yeah, 434. We just showed you mathematically something we already knew. All right, but there it is. Sheesh. That was a long problem. Verify the colors are correct. Provide mathematical support.